All right, welcome back, everyone, to AI Paper Podcasts. Today, we're jumping into a really interesting paper. It's called Learning to Think, Information-Theoretic Reinforcement Fine-Tuning for LLMs.
Yeah, this one caught my eye, too. It tackles a pretty fundamental issue with LLMs.
Right. How they reason. I mean, often they just generate these super long chains of thought, which sounds good, but it's inefficient. Burns through tokens like crazy.
Exactly. And that's where this paper comes in. They're proposing a new framework, L2T, Learning to Think.
And the core idea is using reinforcement learning, but with a twist.
A very clever twist, yeah. They use information theory to reward the model for gaining useful information at each step, and crucially, penalize it for just adding fluff or getting stuck.
So the goal is optimal reasoning, but with fewer tokens, better accuracy and efficiency.
That's the promise.
Okay, so for everyone tuning in, here's the quick takeaway, the kind of short version. This paper introduces L2T, a new reinforcement learning fine-tuning method. It uses an information-theoretic reward to focus on the process of reasoning, rewarding useful steps, penalizing redundancy. They show it leads to better performance, often using significantly fewer tokens across different reasoning tasks and models. Pretty compelling stuff.
Definitely. It really gets at that efficiency problem you mentioned, the token cost, which is, a huge practical barrier for deploying these large models sometimes.
Totally. It's like you have this incredibly powerful engine, but it's just guzzling fuel unnecessarily. The current RL methods, they often just look at the end result, right? Did the model get the final answer correct?
Yeah, it's very outcome focused, black box almost.
Yeah.
It doesn't really incentivize a clean or direct path to the answer.
Like grading a math test just on the final number, ignoring all the working steps.
Precisely. You might get the right answer eventually, but maybe you took this wild, convoluted route that wasted tons of time, or in this case, tokens. There's no reward for elegance or conciseness in the reasoning itself.
So what happens then with just that outcome focus? What did the paper observe?
Well, they point out that models often end up generating these excessively long reasoning chains. It's almost like the model thinks more steps must be better, even if those steps add very little actual value, or worse, just add noise.
And they actually showed this happening. I think they mentioned the OmniMath Benchmark.
They did. They used the DeepScaler 1.5B preview model on OmniMath, and the findings were pretty stark. Models were frequently using more than double the tokens needed to actually solve the problem correctly.
Double, wow, that's a lot of waste.
It really is. And even more interesting, maybe counterintuitive, is that accuracy didn't always keep climbing with more steps. Sometimes it peaked and then actually started to decline if the reasoning chain got too long.
Decline. How does that work? More thinking makes it worse.
They call it context redundancy. Basically, the model figures out the key info but keeps adding steps. This extra stuff just clutters its working context, making it harder to focus, potentially introducing errors.
Ah, okay. Like burying the important fact under paragraphs of irrelevant rambling. That makes sense.
Yeah. And it also highlights that, different problems need different reasoning lengths. Harder problems might genuinely need more steps.
While simpler ones should be quick.
Exactly. But current RL doesn't really adjust for that dynamically. It just sort of pushes for longer chains sometimes.
Which brings us back to needing a better reward system, one that looks at each step. And that's L2T's whole premise.
Right. Learning to think. It's this information-theoretic RL framework.
And the key is that dense process reward, right? Rewarding information gained during the process.
Precisely. Instead of waiting till the end, it assesses the value, the information gain in the model's parameters, step by step, guiding it towards efficiency.
Okay, and you mentioned two parts to this reward. There's a gain part and a penalty part.
That's right. There's the fitting information gain and the parameter compression penalty.
Let's break those down. Fitting information gain. What's that capturing?
That part basically drives the model to focus on updates that are critical for correctness. It rewards incorporating the information that actually helps solve the problem at that specific step.
Okay, so rewarding progress towards the right answer. And the compression penalty.
That's the flip side. It discourages the model from, let's say, over-optimizing or storing redundant stuff. It penalizes holding on to information that's maybe too specific to the current example and won't generalize well, or that just adds complexity without benefit. keeps things efficient.
So lean and mean reasoning. I like it. How do they structure the training to use this reward? You said it wasn't just one long go.
Right. They break down each query response interaction into a session, and that session is made up of multiple shorter episodes.
Episodes being chunks of the reasoning chain.
Exactly. And the crucial part is the reward is calculated and given after each episode, so you get this immediate feedback loop.
Like micro rewards along the way, guiding it step by step. Okay, so the paper outlines 3 stages for L2T: problem reformulation, reward design, fine-tuning. Let's start with reformulation.
Yeah, so reformulation is really about changing how they view the reasoning. Not one long stream, but this hierarchy. A session is the whole interaction, like question to final answer. But within that session, you have these episodes, these shorter reasoning segments.
And segmenting it like that allows them to apply the reward more frequently.
Precisely. It makes calculating and applying that dense process reward feasible after each chunk of thinking.
Okay, stage 2, reward design. This is the core, the information-theoretic magic. How is it calculated?
This is where it gets interesting, yeah. They use principles from information theory. After each episode finishes, they estimate the reward using pack-based bounds and the Fisher information matrix.
Okay, pack-based, Fisher information. These sound heavy. Can we get a bit more intuition there for folks listening, maybe the researchers and engineers?
Sure. High level, think of pack-based as a way to connect how well the model does on the training data to how well we expect it to generalize to new data based on its parameters.
Okay.
The Fisher information matrix tells us how sensitive the model's outputs are to tiny changes in its parameters.
Okay.
So by combining these, L2P can estimate how much genuinely new and useful information the model is incorporating in its parameters during an episode versus just noise or memorizing specifics. It's a way to gauge the quality of the learning step.
So it's not just did the parameters change, but did they change in a meaningful way that helps generalization and correctnesses?
Exactly. And a neat side effect is this reward structure helps the model learn when to stop reasoning if the steps are no longer adding value.
Right, avoiding that pointless rambling we talked about. Okay, and then the final stage is the fine-tuning itself.
Yep. Stage 3 is standard reinforcement learning fine-tuning, but using this carefully designed reward. The model is optimized to maximize the total reward across all episodes in a session.
And that total reward includes both the step-by-step process reward and the final outcome reward.
Correct. It aims for both things. Get the right answer in the end, but also get there via an efficient, informative path.
Makes sense. Let's dig just a bit more into that reward formula. The fitting game and the compression penalty, how are they defined from that information theory angle?
Okay, so the fitting information gain, theoretically, it's about the reduction in uncertainty about the correct answer, given the input, after that reasoning episode's parameter update. In practice, they approximate it by looking at how much the model's predicted probability of the correct answer increases.
More constant in the right direction. Got it. And the compression penalty.
That one's defined as the mutual information between the model parameters and the specific context of that reasoning step. High mutual information suggests the parameters are storing a lot of context-specific detail.
Which might be overfitting or just inefficient.
Exactly. So they penalize that high mutual information to encourage the model to learn more generalizable patterns, keeping the parameters compressed in a sense, focused on reusable knowledge.
And the actual reward calculation combines these.
Yes. The process reward RPGK for episode K is basically fitting gain minus beta times compression penalty. Beta is just a knob you can tune to balance correctness focus versus efficiency focus.
And they figured out how to actually calculate this without it being computationally impossible on these huge models, using those Peck-Bayes and Fisher tools again.
Right, that's key. Direct calculation would be way too slow. Theorem 4.2 in the paper explains how they use Peck-Bayes bounds and properties of the Fisher information matrix to get a scalable approximation. It lets them estimate these information quantities by looking at parameter changes and output sensitivity, avoiding the really heavy computations.
Okay, so it's mathematically grounded, but practically feasible. Why do the authors argue this reward design is particularly good?
They list 3 main reasons. 1, relevance. The fitting gain directly ties to solving the problem correctly.
Makes sense.
2, efficiency. The calculation, thanks to the approximation, is relatively cheap per episode. They mention Theorem C.2 in the appendix about the complexity reduction.
Good.
And 3, generality. Because it relies on internal model signals, information gain, and parameters not external, task-specific rewards, it should work across many different reasoning tasks without needing custom reward engineering for each one.
That generality is a big plus. Avoids a ton of manual work.
Okay, so they have this reward, they have the RL set up. How do they optimize the LLMs?
The optimization aims to maximize a combined objective. It includes the final outcome reward, just, basic correctness, plus the sum of all those dense process rewards earned across the episodes.
So maximize correctness, maximize information gain per step, minimize redundancy, all rolled into one.
You got it.
And then the crucial part,
Yeah.
experiments. Did it work?
I ran a pretty extensive set of tests, lots of tough reasoning benchmarks, AMC, Math 500, Minerva Math, OmniMath, also Human Evolve for code.
And different models too. Yep. DeepScaler, DeepSeek R1 distilled Kin in a couple of sizes.
Oh.
They wanted to show it wasn't just a one-trick pony.
So what were the results? Did L2T deliver?
The results look pretty strong, yeah. In terms of raw accuracy, L2T was generally comparable or sometimes slightly better than the existing methods they compared against, like outcome reward, RL, GRPO, or other process reward ideas, MCTS, MRT.
Yeah, okay, comparable accuracy is good, but the promise was efficiency.
And that's where it really shone. They reported significant gains in token efficiency. Often, L2T achieved similar accuracy using roughly half the tokens compared to the outcome reward approaches.
Half the tokens, that's huge. That translates directly to lower inference costs, faster responses.
Absolutely, a major practical advantage. They also found it performed particularly well when the token budget was limited again, very relevant for real-world deployment constraints.
Did they do ablation studies? Like removing parts of L2T to see what mattered most?
They did. And those studies confirmed that both the fitting information gain and the parameter compression penalty were important, removing either one hurt performance or efficiency. They also showed it working on code generation with Human Evolve using Qwen2 7b instruct, suggesting the approach isn't limited to just math problems.
Okay, so let's wrap up this deep dive on L2T. What are the main things our listeners should take away?
I think the big takeaway is that L2T offers a really promising path towards more efficient reasoning in LLMs. By focusing on rewarding the process the information gained at each step and penalizing redundancy, it addresses a core weakness of many current models.
And that information-theoretic reward based on internal model signals feels like a potentially powerful and general approach, moving beyond needing handcrafted rewards for every single task.
Exactly. And the experiments back it up across different tasks, different models. They show consistent benefits in both effectiveness and critically token efficiency.
It definitely makes you think differently about how we should be training and guiding these models, right? Moving beyond just, did it get the right answer, to how did it think to get the answer, rewarding the quality of the thought process itself.
For sure. It opens up some really interesting research directions. How else can we quantify and reward good reasoning?
Absolutely. For anyone wanting the full technical details, the paper and its appendices are packed with more information on the theory, the implementation, the math, and extra results. Definitely worth checking out if this area interests you.
Yeah, to read.
So what are your thoughts out there? Does this information-theoretic way of guiding LLMs seem like the right direction? What other internal signals inside these huge networks could we potentially tap into to make them reason better, faster, or maybe even more creatively? Let us know what you think.